I know the switch. Thanks so much for the introduction. This work is done in Stanford University with Omid Mashiahi, Chima Isha, and Phil Levis. Nowadays, cloud computing is running ever faster in-memory computation on a larger scale. This is introducing new system challenges. For example, this figure shows running the same logistic regression application on more and more nodes. The red bar shows the computation work on each node in one iteration. As we use more and more nodes, because the total amount of computation work remains the same, the computation work on each node will keep decreasing. So ideally, we expect as we use more nodes, the computation will run faster and faster. But in reality, this is not the case. As we actually run this experiment on Spark 2.0 machine learning library, we saw as we use more and more nodes, the execution becomes eventually slower instead of faster. The problem is that the control plane of Spark is introducing greater and greater overhead as more nodes are used. So even if we could have more nodes, the execution can run not any faster than 1.33 seconds per iteration. So we look at the problem, and we believe the problem is that the control plane is using synchronous operations between the controller and workers. That is, if we look at the program control flow on worker, we will see at certain points, the worker has to wait for the control messages from the controller. If those messages does not come in time, the worker does not know what task to run. They have to wait. It is fine if there are just a few workers, but as there are more than workers, the controller's load will increase, and workers will spend longer and longer time idle. So the key observation here is that existing control planes use these synchronous operations to decide which worker should run which task. And this is exactly introducing the overhead we saw. Therefore, we propose if we can have a control plane without synchronous operations, we can potentially improve the performance and the scalability. We listed 4 goals for this asynchronous control plane. First, we want to do distributed task scheduling. We want the execution of worker to be totally decoupled from the controller. We want to remove the synchronous operations for better performance. Second, we still want to retain a centralized control plane abstraction for flexibility. We want to have a centralized controller that can dynamically decide which worker runs which tasks. So that it is essential for cloud computing to do things like load migration, load balancing, or dynamic scaling or struggle mitigation. There are also other goals you can see more in our paper, but the key challenge here is that because every worker locally decides what to compute in a distributed way, the worker cannot exactly tell what the worker is doing. And even so, the controller still has to maintain centralized control over which worker runs which tasks. So in summary, our paper proposes the design of an asynchronous control plane and implement the asynchronous control plane in a from-scratch cloud framework called Canary. It consists of 2 key components. First, it is a program abstraction called task recipes that allow workers to locally schedule tasks without synchronous operations. Second, it is a scheduling mechanism called a partition map that allows the control plane to decide how to distribute tasks, again, without synchronous operations. We evaluated the system. We saw this control plane can scale well, running hundreds of millions of tasks on 1,000 cores. And meanwhile, having a control plane abstractions allows it to reschedule tasks simply and fast. We also evaluated the systems across a couple of data analytics benchmarks. We saw the system can match the performance of those without control plane at all. This means the control plane is imposing almost negligible control plane overhead. At the same time, it can reschedule tasks very fast. And finally, we saw that the efficiency of the control planes allow us to use very fine-grained tasks to help improve the load balancing, which gives about 2 times speed up. I will first give you some background about what exactly is a control plane. This diagram shows an example control plane architecture. It starts from the user who submits a job, which is an instance of application. And then the control plane accepts the job and tries to split the job into units of tasks to compute in parallel. Then the control plane asks the resource manager what nodes to use to run those tasks. Here, the resource manager can be, for example, Mesos and Yarn. And then finally, the control plane dispatches tasks to all the nodes. And here, the control plane abstraction makes it simple to reschedule tasks because the mapping between tasks and nodes are dynamically generated by the control plane. But this exactly control plane using synchronous operations to implement the control plane is introducing the performance bottleneck. So we want to remove those synchronous operations. The way we do that is to introduce a new program abstraction called task recipes. A recipe consists of a function to run, data to read or write, and also a set of preconditions. If those preconditions are satisfied, a task can start running. In other words, this task recipe declares not only what task to run, but also when those tasks can start running. This same set of recipes that describe a job will be installed on every worker. So every worker can check the preconditions of those recipes against the data it has. If those preconditions are satisfied, the worker will immediately spawn and execute the task. In this scheduling process, the controller is not involved at all. I would also like to mention these task recipes are statically compiled from sequential program before job starts, so it is hard to support dynamic program, for example, for interactive usage. The most important part in task recipes are those preconditions, because these preconditions ensures tasks are executed in the correct order. In our system, we allow data to be mutable because we want to avoid overhead of copying data. This means the same data object can have multiple versions, and the function might read or write the wrong version. So this is why we have these preconditions to order those reads and writes. We have three preconditions. So for example, if a function writes a data partition, the preconditions will specify the last writer to that data partition to make sure this function reads the right version. Or if a function reads a data partition, the preconditions will specify how many readings should happen to avoid overwriting a version too early. And for messages exchanged between tasks, because one message is only written once, there's no versioning issues, so the preconditions just specify the number of messages to receive. I would like to give you a more concrete example. This is a logistic regression loop, which keeps reading the training data to compute the gradient and use the gradient to update the weight. This left table shows all the 5 task recipes to spawn all the tasks in this loop. Notice that the first iteration might be slightly different. To differentiate tasks in different iterations, we use a sequential stage number to differentiate the tasks, as shown in the parentheses. This iteration starts with the broadcast task that reads the weight and set broadcast weight value. Then this recipe for compute will say, once a message is received, a function can start running, reading the message and compute the gradient on top of a training data partition. Notice that this same recipe can be used to spawn both of the data parallel tasks, so this can be scalable. And similarly, this recipe for reduce will say once 2 messages are received, it can sum up the value of those messages and then compute the gradient and write to the gradient. Here, the preconditions for the gradient is not super interesting, so I omit them. And then this recipe for update will read the gradient and write to the weight. Here, the preconditions enforce the reduce task will run before this update task. And also, it ensures this function will not run again and again, because once this task completes, the preconditions can no more be satisfied. At the end of this iteration, the recipe for again will spawn a task that decides whether to run another iteration or not. And also, I want to mention that because of how the preconditions are written, this again task can run in any order and be reordered with the update task. And finally, this is loop. In case the again task generates a control message that indicates another iteration is needed, this broadcast task, this recipe will trigger another task that spawns a whole new iteration. So next, I will show you how we achieve a centralized control over task distribution. As I just talked about, by using task recipes, we allow each worker to locally schedule tasks. But it did not solve the problem of how to control the task distribution, which means still at this point, we does not have a control plane. So the way we do that is to rely on the execution mechanism of task recipes, because a recipe will only spawn a task by looking at what data it has and checking those preconditions. So if we could use the control plane to decide the data distribution, and then how recipes trigger tasks will change accordingly. And then the task distribution will change accordingly. The way we did that is we used a data structure called a partition map that basically describes the data distribution. This partition map can only be updated by the controller so that the control plane can express how data should be distributed. And then every worker will receive this update and asynchronously migrate data to reflect the changes, and task distribution will change accordingly. And in this process, when I say asynchronous because once a worker receives a partition map update, it can be in the middle of running some tasks accessing that data to migrate. So the worker has to decide to wait for those tasks to complete before doing the migration. And all this ordering and scheduling is all happening without the controller's intervention. There's no synchronous operations. And next, I want to show you some evaluation results. We try to compare with two design points about control planes. The first design point is those synchronous control planes. These synchronous control planes use synchronous operations, so the number of tasks they can execute per second are highly limited. They cannot scale well. The second design point are those systems without control plane at all. The way they schedule tasks is that they decide how to statically assign tasks to all the nodes before a job starts. So once the job starts, there's no control plane traffic, there's no dynamic control, and no synchronous operations, so it can scale very well. But downside of this is that in order to reschedule tasks, the user has to manually kill the application and rerun it from the last checkpoint. And I know there are still some ongoing work in TensorFlow trying to solve this problem. So we want to ask, can a synchronous control plane, as proposed by our paper, achieve the best of both the design point? Can it scale well and make the application run faster, and at the same time, can it reschedule tasks very fast? This first experiment evaluates the scalability of our system. It runs a micro benchmark. It tries to run a large number of totally independent and empty tasks on an increasing number of cores. As you can see, as more cores are used, the task rate of this system, that is the number of tasks that can be executed per second, increases linearly. This is because, in this case, every single core in our system is checking the preconditions of those task recipes to spawn tasks independently. Because the task rate is so high, it's very unlikely in practice an application will ever be blocked on the control plane. We try to evaluate how this control plane scalability affects the execution of application. We run the same application logistic regression on a couple of different cloud frameworks with different control plane design. We did a simple hack, try to rule out the language difference. We replaced all the computation codes as busy looping for the same amount of time. So virtually, the computation is running at the same speed. So as a result, this result only shows the difference caused by the system itself. As you can see, canary TensorFlow that can scale almost linearly, running much faster as more cores are used. This is because they use no synchronous operations at all, and the difference here is due to some implementation artifact. And for Spark, it uses one synchronous operations for each task, so it scales poorly. For Nimbus, it's another system trying to reduce the number of required synchronous operations. It uses one synchronous operations for multiple tasks, so it can scale better, but still not as well as Spark, much better than Spark. Finally, we show how our system can reschedule tasks. We run the same k-means clustering application on 64 nodes and compare with TensorFlow. The x-axis shows how much time, shows the time evolving. The y-axis shows the number of iterations that have been executed at that time point. And so the slope of the curve shows how fast the system is executing. As we add a straggler by running a background CPU-intensive process, we see the slope begins to flat out because it is becoming slower. And when our system tries to mitigate the straggler by migrating tasks away from the slow node, it almost takes only milliseconds and hardly can be seen on this figure because the only overhead here is to send the partition map updates to all the workers, and data migration overhead is excluded because we assume data replicas. There are multiple data replicas for one same data partition. But for TensorFlow, in order to migrate tasks away from the node, it has to kill the application and restart from the last checkpoint. This can take seconds. And if the cluster is very unstable, this can cause a very big overhead. So to conclude, we design a new asynchronous control plane and implements the design in a new cloud framework. It consists of two key components, a new program abstraction called task recipes, and a new scheduling mechanism called a partition map. It scales reasonably well and also retains the flexibility of having a control plane to do all the scheduling functionalities. And this concludes my talk. Thanks.
So thanks. We have time for a few questions.
Your task recipes, those are supplied by the programmer?
Not exactly. We have an interface for user to write a sequential program, and the runtime automatically constructs those recipes from the sequential program because it's very error prone to ask a user to write it, because if just something happens wrong, it's very hard to debug it.
Okay, thank you.
I have one question about task recipes. How many of them have you implemented, and is it really hard or not to implement them? How many different task recipes have you implemented, and is it hard for the developer to provide them or not?
So you're asking how many recipes I have programmed?
Yeah.
Yeah, so for the same application, it is described by multiple recipes, and we try to evaluate, we try to write this program abstraction for data analytics frameworks, also some scientific computing applications. But the runtime standard the recipes, the paper describes a more interface of how to program those sequential program, which can be translated to those recipes.
Any more questions? No? Okay, so let's thank again the speaker. Oh, okay, the next speaker? Yep. Okay, so the next paper is 3 sigma distribution-based cluster scheduling for runtime uncertainty, and the paper will be presented by Yoon-Woo Park.
Morning. I'm Junu Park from Carnegie Mellon University, and today I'll talk about 3 sigma, a cluster scheduler that uses full runtime distributions instead of single-point runtime estimates to robustly handle runtime uncertainty. This is in collaboration with Alexei Tumanov from UC Berkeley, Angela Jiang, Michael Kozuchi from Intel Labs, and Greg Ganger. For those who are not familiar with cluster scheduling, I'll describe how it works in a nutshell. In this model, users are submitting many different types of jobs, ranging from long-running services to the batch analytics jobs to the cluster scheduler. Cluster scheduler then matches these jobs to the available machines in the cluster. Now, cluster scheduling has been around for a while, but the challenges have gotten bigger in recent years because of the increased hardware diversity and increased practice of mixing different type of workload on the same shared hardware. And here's the overview of my talk. I'll briefly talk about how best recent schedulers rely on runtime estimates to handle increased hardware diversity and workload mixing, and why it is not very robust to the runtime uncertainty. Then I'll describe my system 3 sigma, which can cope with runtime variation robustly by using the runtime distribution instead of point estimates. And I'll demonstrate that with experimental result, how Three Sigma is more robust than the previous approaches. So many recent schedulers now use more sophisticated scheduling algorithms that use runtime information. Using the runtime allows schedulers to compare trade-offs, such as whether to run the job right away on a slow machine versus waiting for the faster machine. And it can also increase the utilizations by packing jobs more tightly and using more information. It can also prioritize jobs to meet their deadlines. The problem is that these schedulers tend to rely on something called runtime estimate instead of full runtime information. For example, job 1 will run for 100 seconds. This is usually an educated guess or prediction from the previous runs of the job. Problem is, there are inherent variabilities in the real jobs running in the cluster. And here's the full statistics of runtimes we have about a class of job, which this job comes from. The plot is actually a histogram of runtime of jobs with same job name in the Google trace. A lot of times, these jobs will run for 100 seconds, but many other times it can just run for 10 seconds or even 1,000 seconds. And the point estimate is just a tiny part of this possible range of runtimes. And providing a point estimate to the scheduler is like taking this tiny point out of full range of possibilities. And whoa. Oh, my mistake, sorry. So providing the point estimate to the scheduler is like taking this tiny point out of full range of possibilities and covering up everything else like this. You see what happened here. I covered up the most of the information and scheduler only gets this tiny bit of information. If our point estimate is perfect or nearly perfect, it may not be a problem. But sometimes point estimates can be off by a large margin. For example, if the runtime is overestimated, meaning the estimate is larger than the actual runtime, the scheduler may think the job is too hard and may not even try to run the job at all. On the other hand, it could be an underestimate, meaning the estimate is shorter than the actual runtime, and the scheduler may think the job is too easy and start the job too late and miss the deadline. All of these problems will go away if the scheduler can use the full runtime distribution instead of the point estimates. So Three Sigma is the scheduler that has been enhanced to use full runtime distributions. By using runtime distribution, it is more robust to unpredictable runtimes and variabilities. It uses following mechanisms to use the runtime distribution. First, it considers the expected utility in scheduling the job, the expected benefit of scheduling a job, reflecting the odds of each possible outcome according to the distribution. It also considers each possible outcomes of running jobs in computing the amount of resource to be consumed by the running, amount of resource consumed by the jobs. Finally, it also needs the mechanisms to handle imperfect distributions, because sometimes the job behaves differently from the distribution. And here's the architecture of our system. It's composed of two main components called Three Sigma Predict and Three Sigma Sched. Three Sigma Predict associates a runtime distribution for each pending job. It does this by first generating distribution from several groups of similar jobs and choosing the best candidate distribution that has performed well in the past. And Three Sigma Sched makes a scheduling decision with distribution. In this talk, I'll focus more on the scheduling component, Three Sigma Sched. Before I describe how Three Sigma makes the scheduling decisions, let me describe the workload I will use in this presentation. It is a mixture of SLO and best effort jobs. SLO, service level objective jobs, are jobs with a hard deadline. And best effort jobs are latency sensitive jobs that does not have any deadlines, but we want them to finish as soon as possible. And we consider the SLO jobs to have higher priority. Our primary goal is to meet as many deadlines as possible for SLO jobs, but at the same time, do as many best effort work as possible. So here's the scheduling algorithm when we have the precise knowledge of the runtime, how long the job will run for. The scheduler will first generate the possible scheduling options in terms of available resource type in the cluster and the potential start time of each job. We'll assign a utility to each scheduling options, a value determined by the completion times of the options. For example, SLO jobs will have 0 value after deadline, and it will be a lower value for later start times for best effort, latency sensitive best effort jobs. The scheduler will choose the best combination options across all the jobs so that it maximizes overall utility and while making sure everything fits within the cluster. Now, how would we schedule with distribution? Having a distribution instead of single point runtime means that we'll have multiple possible completion times and the utility value for each of the options. So instead of maximizing the overall aggregate utility, the scheduler will aim to maximize the expected utility, the utility weighted by likelihood of runtimes. Likewise, the scheduler will consider each job's possible runtimes in order to when it's making sure everything fits within the cluster capacity. And here's an example of how we can use a distribution to evaluate scheduling options with expected utility. Imagine a job that runs for 1 time unit for 75% chance and 2 time units otherwise. Imagine this job also has deadline in 3 time units from now on. Here on the bottom, we'll plot the expected utility for this job for each of the potential start times of the job. So in the first case, let's assume if we start the job before 1 time unit. We see that we'll always meet the deadline if we start it there, so it will have a full utility value, capital U. So the expected utility will be the full utility value. Now, if we start the job later than 1, but before or on at time 2, we'll see that we'll meet the deadline if we're lucky with 75% chance. We'll note that and mark the expected utility will be 0.75 U. And if the job is started later than 2, we'll always miss that deadline and the expected utility will be 0. Comparing these 3 options, we can see that it is optimal to schedule the job before or on at time 1 and suboptimal to schedule before time 2, and it's impossible to finish the job on time if we started later than time 2. Now, what if we have a point estimate? For example, 1 time unit using the median. On the right side, we have what the scheduler thinks the job will do if we have given the 1 time unit a point estimate. It sees that between time 1 and time 2 would be same as starting before time 1, which is not really the case, and scheduler will make mistakes based on that wrong information. Lastly, I want to show some experimental results that compares our system to previous approaches. We ran experiments on a real cluster with 256 nodes, worker nodes, and the workload is derived from the Google cluster trace, 500 jobs, 2-hour experiments, mixture of SLO and best effort jobs. We report two success metrics: SLO miss rate, which is the percent of SLO jobs that miss the deadline, and goodput, which is the amount of work completed by the workers in the experiments measured by the machine hours. We compare 4 different scenarios. 3 sigma is our system that uses distribution coming from a 3 sigma predict. And next 2 scenarios, point perfect and point real est, both are a point estimate based scheduler. And for perfect variant, we provide the actual runtime of job as an estimate. So scheduler knows exactly how long the job will run for. For real est, we use the estimate coming from a predictor based on the history of previous jobs. We also compare against Prio, a priority-based scheduler that strictly prioritizes SLO jobs over best effort jobs. And it does not use any runtime knowledge. We expect 3 sigma to be very robust to the uncertainty and perform very close to the hypothetical scenario, point perfect. We also expect that 3 sigma to be much better than point real est, which only uses limited amount of runtime information, and Prio, which does not use runtime knowledge at all. Here we compare the SLO miss rate for the systems. On the x-axis, we have different systems, and on the y-axis, we have those SLO miss rate. Lower is better for this graph. We compare 3 sigma to the point perfect, the hypothetical scenario, and we see that it performs very close to the point perfect. We also, on the other hand, point real est performs much worse compared to 3 sigma. This shows that point estimate-based schedulers are not very robust to the runtime uncertainty. 3 sigma also performs better than the Prio, where we strictly prioritize its SLO jobs over best effort jobs. And here we compare overall goodput achieved by the system. We see that 3 sigma completes as much SLO job as point perfect, while doing much more work compared to point real est and the Prio. There are other aspects of 3 sigma in paper I didn't have time to discuss. As a motivation, we analyzed the runtime variability of Google cluster trace and 2 new cluster job traces that will be released to public soon. We also have experimental results with these traces. And there are other mechanisms, such as how to compute the expected resource consumption using the distribution, and 3 sigma predict how we associate a runtime distribution for each pending job. And then there are mechanisms to handle imperfect distribution as well. So in conclusion, I described how best recent schedulers tend to rely on runtime information, usually in the forms of point estimates, such as mean or median of the observed runtimes in the past. There are problems when the runtime estimates are inaccurate. 3 sigma, our system, copes with runtime variation robustly because it leverages distributions instead of point estimates. The result is that we perform as good as the perfect estimates and much more robust than the previous approaches. Thank you, and I'll take any questions.
So thanks. We have time for a few questions. Yes.
Hi, Björn Brandenburg of MPI Software Systems. Interesting work. I was wondering, how do you handle correlated runtimes, and how important is that to get good performance?
Correlated runtimes meaning
if you have, just the distribution doesn't tell you whether 2 jobs always run or overrun at the same time or not, or it might be time dependent. So jobs in the morning always run longer than jobs in the afternoon.
So you're assuming that the job submitting at the morning is roughly same with each other?
Yeah, so let me ask differently.
Yeah.
Do you assume that these distributions are all independent?
Yes, I assume everything is independent for now.
And the trace bears that out?
Sorry? I didn't hear that.
And I assume this, I mean, that the trace shows that they're independent, and this is why it works well.
So I think we can talk offline a little bit, but so we use a different type of features in computing the I think it's related to how we come up with the distribution. And we do not use a feature like what's the hour of the day the job was submitted in computing that distribution. So I think it takes a note of that, but I can talk to you more
Thank you.
in the poster session.
Hi, Gilles Wonepoel, EPFL. How well would they scale to a larger cluster? Your experiments are with 256 nodes. How would it work, for instance, in a system with 10,000 nodes? Would it still be possible?
So we do have a micro benchmark in the paper that has the same size as the Google cluster trace. I think it's in the order of 10,000 nodes magnitude, and it still works well in that scenario.
Yep.
Hi, Menak from UIC. So I was wondering, can you talk a little bit more about how your system is different from Rayon, which is, you call it a point real-time estimate system, and why is that different from 3 Sigma?
So the Rayon uses only the point runtime knowledge, meaning that it will take in runtime, how long this job will run for, like 100 seconds, provided by the user in the reservation time.
But I think it takes us more of a skyline instead of just a point estimate, right? Like it takes it over time, how long, like how much resources will be taken over time.
Right. So in terms of resource resource required by the jobs, we assume that it's given by the user, and the jobs will follow that resource usage.
Julia Lawal, in Rea, how does it relate to what's done in real-time systems with probabilistic worst-case execution time?
Probabilistic. So the worst, to use a worst-case runtime, I think it's it's different in that it's always going to assume the worst-case runtime, meaning that it will always result in conservative.
No, there's a probability. What's done today is probabilistic, so there's a probability associated with the proposed worst-case execution time.
So I know there are systems that uses expected benefit of using the job, but I guess my system is different. Well, so there are other components such as how to use the distribution to compute the expected resource consumed by the jobs, and then the mechanism to come up with a runtime distribution. Or honestly, I'm not aware of, or what do you say? Maybe we should talk offline about it, because
Okay,
I'm not
that's fine,
sure.
thank you.
Yeah, I'm not sure if I'm in the right mind. If I understand you correctly.
This is Mitra Nasri from Max Planck. When we are dealing with hard real-time systems in real-time community, we consider sort of reservation systems in order to protect hard real-time systems, which are usually safety critical. We don't want them to miss deadline. Did you consider comparing with those type of solutions, or you just compare with best effort scheduling policies in your approach, in your work?
So hard deadline system. So we assume that I'm more thinking of the deadline in terms of the cloud data centers, like there's like latency, or we're more thinking of the granularity of a few seconds or few minutes of the jobs, and the deadline coming in like a couple minutes or hour. So I think but we still consider hard deadlines and mixture of latency sensitive jobs. But I think we operate on a different scale of time. I think that's the main.
Real-time systems are not about very fast systems. I know that the time is running, so I just give the microphone. We can talk offline.
Yeah.
Okay, so let's thank again the speaker. So the third speaker is Yanghua Peng. Is from the University of Hong Kong, and is going to talk about Optimus, which is an efficient dynamic resource scheduler for deep learning clusters.
Thank you for introduction. Good morning, everyone. I'm Yang Hua from the University of Hong Kong. Today, I'm going to present Optimus, an efficient dynamic resource scheduler for deep learning clusters. And this is a joint work with ByteDance Incorporation. In recent 5 years, we have seen great progress and successful applications of deep learning in various AI domains, such as speech recognition, Amazon Echo, object classification in autonomous car, or machine translation in Google Translate app. The combination of big data and deep neural networks significantly improve learning accuracy, but suffers from a long training time. Therefore, many distributed machine learning frameworks have been proposed to accelerate the training process, such as TensorFlow, MXNet, and PaddlePaddle. Most distributed machine learning frameworks adopt the parameter server architecture. In this architecture, the deep neural network, or the model, is partitioned among multiple parameter servers, and the data is split among multiple workers. And the training is an iterative process. In each iteration, each worker reads a mini batch from its data and then does forward and backward propagation to calculate gradients. Then, the gradients are pushed to parameter servers. After receiving gradients, the parameter servers update the model or the parameters based on some optimization algorithm like a stochastic gradient descent. Then each worker pulls the latest updated parameters from parameter servers and starts next step. And our work focuses on the parameter server architecture. As we know, many IT companies have been operating large-scale machine learning clusters with hundreds of GPU servers. From our experience, the current scheduling practice is far from optimal. The first reason is static allocation. That means a fixed number of parameter servers and workers are allocated to each job upon the job's submission. That means the resource configuration of a job is unchanged during training. And this may lead to low resource utilization, because when the cluster has more available resources, then the running job cannot benefit from these resources. And the second one is that the job size is unawareness. That means from this figure, so different models have different training time, and it varies significantly from like tens of minutes to hundreds of hours. So considering job size in scheduling is very important, as a long job may block a series of short jobs and cause a long job completion time. And the third is that the resource configuration of job is manually specified by the job owner upon job submission. And this may lead to suboptimal resource efficiency. Let's consider a case where there are 20 parameter servers and workers in total. So here, if the number of parameter servers is x, then the number of workers is 20 minus x. So this figure shows the training speed when we vary the number of workers and the number of parameter servers. So the maximum training speed is achieved when there are 8 workers and 12 parameter servers. So this optimal point is very difficult to find for users because it's not same for all jobs. Consider another case where we increase the number of workers but keep the ratio of the parameter server to worker to be 1/1. So we see that increasing resources doesn't lead to linear speed up and can even slow down the training. So to address the above limitations, we propose Optimus, a customized job scheduler in deep learning clusters. And our approach is to exploit deep learning and the parameter server architecture characteristics to improve job scheduling and resource allocation. So when we train a deep neural network, we first collect its training loss and use the training loss to estimate its convergence curve. That's how many more training steps are needed for model convergence. At the same time, we can collect its training speed and build a resource speed model. And the resource speed model is a speed function, so it tells you, given a certain amount of resources, how many training steps can be finished in unit time, like in 1 second. So with the remaining steps to converge and the speed function, we allocate resources to each job to minimize the average job completion time. And given the job resource requirement for each job, the task placement module tries to find the optimal placement for tasks like parameter servers and workers. And the resource allocation are adjusted in a dynamic way and in a reinforcement way. So as the training goes, we can collect more training statistics like training loss and training speed and build a more accurate performance model and make better scheduling decisions. So let's first look at the convergence curve. So here we observe that most deep learning jobs use stochastic gradient descent, SGD, to update parameters. So since SGD converges at a rate of 1/k in terms of step k, so we can utilize this property and estimate the training loss L as a function of step k. In this formula, L is the training loss, and k is training step. Beta 0, beta 1, and beta 2 are coefficients. And this figure shows an example of the training loss data points and the fitted curve. So to build this model, we need to calculate the value of beta. Our approach is online fitting. So we first collect and pre-process training loss data points, and then use a non-negative least square solver to find the beta that can best fit the data points. And after calculating beta, we can use this formula to estimate the remaining steps to converge. And one problem here is the estimation error. So this figure shows how estimation error changes as training goes. So we see that as training goes, we can collect more training data, and then the model is more accurate, and the estimation error is smaller. Next part, resource speed model. So we have built a performance model for parameter server architecture. And in this model here, T is the training time, 1 step. And the second item is gradient computation time at worker. And the third is data transfer time between parameter servers and workers, and the wait update time at parameter servers, plus some extra overhead caused by like a straggler issue or control message between parameter servers and workers. And based on this performance model, we can derive the training speed F as a function of the numbers of parameter servers P and the number of worker W. Here, FPW is the training speed given P parameter servers and W workers. And P and W are variables, theta are coefficients. So to derive this formula from the above formula, we simply replace unknown constants in the above formula, like T forward, T back, B, or T update with unknown coefficients theta in the below formula. So to calculate the value of theta, we adopt a similar fitting method. We collect the data points P, W, F from several sample runs, and then use the fitting method to calculate theta. Generally, we can get a less than 10% error using 10 data points. And these two figures shows a speed function when training ResNet model. And the third part is resource allocation. So our problem is to decide the numbers of parameter servers and workers for each job based on the above performance model. And our scheduling objective is to minimize job completion time. Here, Tj is the remaining time, is the remaining completion time of job j, and it equals to Qj divided by F. Here, Qj is the remaining convergence steps predicted by the convergence model, and F is the training speed estimated by the speed function. And we have also considered the resource capacity constraint here. This problem is a non-convex and integer programming problem, and it generates NP hard. So we design a greedy algorithm. And we first define the marginal gain as the reduced job completion time per unit resource. That's how much job completion time can be reduced if we allocate one more resource to the job. And the algorithm works as follows. So in each iteration, we try to increase one parameter server or one worker for each job and calculate the corresponding marginal gain. And then the job with the highest marginal gain is selected, and we allocate one parameter server or worker, depending on which brings higher gain. And we then update the marginal gain of the selected job and available resources in the cluster. And the algorithm stops when some resource is used up or the marginal gain is non-positive. The last part is task placement. We need to decide the optimal placement given the numbers of parameter servers and the workers decided by the resource allocation part. So generally, we need to minimize communication overhead. That's the cross-server data transfer between parameter servers and workers. So we propose two principles. The first is that we need to co-locate parameter servers and workers. And the second principle is that each physical server holds the same number of parameter servers and workers. And we have designed a placement algorithm based on these two placement principles. And when implementing the system, we've identified a load imbalances on parameter servers in MXNet and in TensorFlow. And the issue is that the parameter assignment among parameter servers is uneven. So we propose a best fit decreasing algorithm to balance the load. And for distributed training, we use MXNet. And to adjust the resource allocation, we first checkpoint the model and then restart the job. And we use Kubernetes as cluster schedulers and run parameter servers and workers in containers. The Optimus scheduler is deployed as a normal pod in the cluster. For evaluation, our test bed includes 13 GPU and CPU servers. The trace includes 9 types of deep learning jobs with different model sizes, network types, application domains, and data sets, as shown in this table. And we use dominant resource failures, DRF, and the Tetris schedule as baselines. And the performance metrics are average job completion time, short for JCT, and max span. So we first compare Optimus with DRF and the Tetris scheduler and the different job arrival distributions. The distributions include uniform distribution, Poisson distribution, and a Google trace. The y-axis here is a ratio. So it's a ratio of the dominant resource fairness or Tetris metric over Optimus metric. And if the ratio is larger than 1, that means its performance is worse than Optimus. generally compared to dominant resource fairness, our scheduler achieves over 1 time speed up in job completion time and 0.4 speed up in make span. And this figure shows the normalized CPU usage of parameter servers in each container. So the blue line here is Optimus. We see that it achieves higher CPU usage. So it means that Optimus can utilize resources more efficiently than the other two schedulers. We have also analyzed the performance contribution of each component, including resource allocation algorithm, task placement scheme, and parameter server load balancing algorithm. We see that the three components contribute to the performance by about 62%, 17%, 20% respectively. And in summary, Optimus is a customized job scheduler targeting high training performance and resource efficiency in deep learning clusters. And at its core is a performance model for deep learning jobs. And for future work, we plan to extend Optimus to handle more deep learning or machine learning workloads. And also, we want to investigate robust scheduling to handle inaccurate performance models. Thank you. Any questions?
Gilles from Tsinghua University. Great work. And currently, most of the machine learning people customize their learning rate. So how do you handle this case?
In our scenario, the learning rate is fixed during training. So we assume hyperparameters of the model is fixed, and we do not touch that part.
Okay, I see.
Peter Pizzo from Imperial College London. So can you say a bit more how robust your resource speed modeling is when I look at, for example, different synchronization strategies? So if I were to apply this to a different distributed machine learning framework that happens to have a different way of synchronizing with parameter servers, how much work would it be to update your modeling?
We have built two performance models. One is for a synchronous model, and one is for a synchronous model. And actually, the prediction error for a synchronous model is larger. It's higher. It's about for convergence, it's about 20% error, and that may cause about 15% of performance loss in scheduling.
Okay, thank you.
Other questions? No. So let's thank again the speaker. Oh, no. Okay. So last talk of this session it will be given by Panagiotis Garifakis, and his good news is from Imperial College London, not from Greece. Oh, I assume you're from Greece. And he's a third-year PhD student. So he's going to talk about Medea, that is a scheduling for long-running application in shared production clusters.
Thank you. So hello all. This talk is about Medea, cluster manager with powerful placement constraints. As we also heard from previous presentations, compute clusters today are changing. From running traditional analytics applications with short-running containers such as MapReduce, Scope, and Tez, to interactive data-intensive applications, streaming systems, latency-sensitive applications, and machine learning frameworks. This is a growing class of applications with consisting of containers running for durations ranging from hours to months, and we refer to those applications as LRAs. While we could use dedicated clusters for the deployment, in reality they are sharing cluster resources with traditional analytics tasks, so their placement is much more complex. We did an analysis across 6 analytics clusters inside Microsoft, and as you can observe in the figure, at least 10% of each cluster resources was used by LRAs, while 2 of them were used exclusively by them. Machines, in that case, for LRAs were picked either statically or randomly, And as LRAs occupy a significant amount of resources, their placement is quite important. So let's talk about the typical LRA scenario, where we have 2 racks consisting of 4 node JITs. These nodes are upgraded in groups, which are different than their physical groups. And this is the reason we have 2 different upgrade groups or upgrade domains here, namely A and B. We have a bunch of analytics applications running in the cluster, as well as LRAs. For example, HBase, a key-value store with data partition in memory across machines. And Storm, a streaming application reading data from HBase. We also have some placement requirements for the containers. For example, for Storm, we might want to increase its performance. A way to achieve that would be to collocate Storm containers in the same rack as HBase to reduce network traffic. We also want to achieve cluster objectives. For example, minimizing resource fragmentation. Avoid cases where the resources left in a node are not enough for a single container instance. At the same time, for HBase, we might want to increase its resilience. A way to achieve that would be to place containers across upgrade domains so they don't fail together, so increase its availability. So all these requirements I described are essentially placement constraints. And our goal in this work is to achieve diligent, careful placement of containers through constraints. To see the impact of availability, we did an analysis in a Microsoft cluster with groups similar to our example. So as you can observe in this figure, showing the availability of machine percentage over a period of 4 days, the total availability is always below 10%. However, in a specific node group, it can spike up to 100% due to maintenance, machine maintenance, OS upgrades, or machines being repurposed. With a random placement, an LRA might lose multiple containers at a time. So the placement is quite important. Our goal is to provide placement constraints, and towards that goal, we faced several challenges. The first challenge was how to relate containers to node groups. The second challenge is how to express different types of constraints related to LRAs. And finally, how to achieve high-quality placement without affecting the task-based jobs which are traditionally running in the cluster. Media is our cluster scheduler tackling those challenges with support for container tags and logical node groups to relate containers with node groups, with expressive cardinality constraints that can capture a wide variety of constraints, and following a 2-scheduler design that can achieve both high-quality placement and low scheduling latency. Starting with the container tags, we use these container tags to be able to refer to either containers or group of containers. And as you can see in the figure, we can use these container tags to describe application types, such as a key-value store, application roles, such as HBase master, resource specification, such as memory critical, and global application IDs. Using those container tags, we can refer to any LRA container that is currently deployed in the cluster or will be deployed in the future. We also use logical node groups to be able to refer to dynamic node sets, dynamic node groups that are changing over time. These logical node groups can describe both physical groups, such as a node or a rack, or logical groups, such as an upgrade domain. Inside these logical groups, we associate nodes with the container tags that live there. For example, node 1 here will be associated with all the Storm container tags, and node 2 will be associated with HBase container tags. Then, in a hierarchical manner, these container tags will also be related with the upgrade domains that they are related to. For example, here, this upgrade domain will be related with both Storm and HBase container tags. Using these logical node groups, we can express high-level constraints, such as spreading containers across upgrade domains without actually knowing the underlying infrastructure. So this is a quite handy feature. Now that we can relate containers with node groups, we can start defining our constraints. For our constraints, we want them to be generic enough and capture a wide variety of cases. We want to define, we want, for example, to place our containers with source tags in a node part of a node group in such a way, and this is our placement constraint, that there is at least a minimum, at most a maximum, containers with a specific target tag. And this is our form of constraints, our simple form of constraints. Using that form of constraints, we can define a variety of cases. For example, we can require to place a container with a tag storm in a rack node group where there is at least one H-based container and at most infinity H-based containers. And this is a typical affinity constraint. We can also define more generic constraints like cardinality constraints. For example, we can require the placement of a container with a storm tag in a node set where there is at most 5 storm containers running. So surprisingly enough, with a simple cardinality constraint, we can define a wide variety of cases. And we can create more complex expressions, combining a lot of those using Boolean operators. Now that we can define our constraints, the question is, how do we make scheduling decisions based on those constraints? And for that, we use a two-scheduler design. So we use a traditional scheduler for task-based jobs and an optimization-based scheduler for LRAs. The reason for using 2 different schedulers is because we have 2 different goals. For the task-based scheduler, we want to make fast allocation decisions, and for the LRA scheduler, we want high-quality placement. So again, there's a trade-off here between high quality and low scheduling latency. Now that we have these 2 schedulers, we could actually use both to make allocation decisions, but this could cause state inconsistencies. Imagine, for example, both the LRA scheduler and the task-based scheduler grabbing containers from the same node. This could cause conflicts. This is the reason we went for a simpler design where the task-based scheduler is the only responsible for the final container allocations. So let's talk about the life cycle of our schedulers. Users submit tasks through the task-based scheduler, who considers them one by one and does the container allocations. Users also submit LRAs along with their placement constraints through the LRA interface to the LRA scheduler. The LRA scheduler contacts the constraint manager, who is aware of the whole cluster constraints, cluster node tags, and cluster node groups. And then periodically, using an ILP scheduling algorithm, considers multiple containers at a time and makes scheduling decisions. These scheduling decisions are then forwarded to the task-based scheduler, who makes the final allocations. So in Meda, using this 2 scheduler design, we can satisfy constraints without actually affecting the task-based jobs which are traditionally running in the cluster. For our implementation, we built Meda as an extension of Apache Hadoop Yarn, and our code is actually part of the current Hadoop release 3.1.0. We introduced APIs for clients to define their own constraints, and all the Medea's components I described previously are part of the resource manager. So we also support pluggable scheduling algorithms, so users can actually implement their own scheduling logic to place LRAs. For the task-based scheduler, we used Yarn's capacity scheduler, but any other scheduling logic could be used there. For example, the first scheduler could be used. Moving to the evaluation. For the evaluation, we want to answer mainly 3 questions. The first one was, what is the impact of cardinality constraints in LRA performance? Are they actually important? The second question was, what is the 2 scheduler benefit in terms of scheduling latency? And the third one is, what is the benefit of Meda in a large scale environment? So for the first question, we studied the impact of cardinality in LRA performance. And to do that, we deployed a machine learning workflow running 1 million iterations with 32 workers. And as you can see in the x-axis, what we did is we varied the maximum workers collocated per node. This is a cardinality per node constraint pretty much, with 1 being anti-affinity and 32 being affinity. And affinity and anti-affinity are the constraints that are actually supported by state-of-the-art schedulers today. On the y-axis, you can see the runtime of the workflow, so lower is actually better. We first deployed TensorFlow in a low-utilized cluster, where about 5% of the cluster resources were used. And as you can see, collocating up to 4 workers gave us the best results. So affinity and anti-affinity did not give us the best results, but collocating up to 4 workers gave us the best results. Then we deployed the same workflow in a highly utilized cluster, where about 70% of the cluster resources were used. And as you can observe, collocating up to 16 workers could reduce the runtime by 34% compared to anti-affinity and by 42% compared to affinity. So the key takeaway here is that affinity and anti-affinity are not enough, so cardinality constraints are important. For the 2 scheduler benefit, what we did is we measured the scheduling latency, where we kept the cluster fully utilized and we varied the percentage of resources used just for LRAs. First, we used a single scheduler where we optimize both the placement of short and the long-running containers. And this is the scheduling latency we got for container allocations. Then we compared this with Media's two-scheduler design. In Media, we optimized the placement only of long-running containers. As you can observe, when LRAs occupy a portion of the cluster, for example, 20%, the latency, scheduling latency is 9.5 times lower than optimizing for the placement of both. So in Media, what we do is we use expensive scheduling logic only where it matters the most, only for long-running containers. Finally, we deployed Media in a large-scale cluster consisting of 400 machines, and we deployed a bunch of workloads there. So we deployed 50 HBase instances with 10 workers each, 45 TensorFlow instances with 8 workers and 2 parameter servers each, while we're also running some batch production analytics workloads, occupying 50% of cluster resources. We also used some constraints. We also required some constraints. For example, we required each LRA instance to be placed on the same rack to reduce the network latency, while we also handpicked the best cardinalities that gave us the best performance. For example, we collocated up to 2 HBase workers on the same node and up to 4 TensorFlow workers on the same node. This figure actually shows the TensorFlow runtime in minutes when we use different schedulers for that deployment. So first, we deployed all the applications using Yarn, which is our production-ready, constraint, unaware scheduler. So you can see that we have a quite wide distribution of runtimes, where the median is around 500 minutes. Then, we deployed all the same applications using Kubernetes. We implemented Kubernetes scheduling logic on top of Yarn, and what Kubernetes does is it supports affinity and anti-affinity, but considers a single container at a time. And as you can see, by just adding some placement constraints, we managed to reduce the runtime by 58%. Then, since we saw in previous examples, we considered that cardinality is really important, so we extended Kubernetes scheduling logic to support cardinality. And as you can see, even though some applications did better and some others did worse, the median runtime is still the same as plain Kubernetes. Then we deployed the same applications using Media. In Media, we support cardinality constraints, but we also consider multiple containers at the time. As you can observe here, we have a much tighter distribution, and also the 99th percentile managed to be dropped by 54% compared to plain Kubernetes. So using all those features, Media manages to improve performance, both performance and predictability of LRAs. So to sum up, I presented powerful constraints are required to unlock the full potential of LRAs. I presented Media, a cluster manager following a two-scheduler design with support for expressive and high-level constraints that does not impact the latency of task-based jobs. Media is actually open source, so feel free to download and play with it, define your own constraints. And with that, I would like to conclude, and I'll be happy to take any questions.
Thanks. So, time for several questions. Yeah. John?
Good morning. Really nice work. This, by the way, is why we put multiple schedulers into Omega. Yay. Cool. Let's talk offline about some of the issues around description of Borg, but I was interested in one. There's a couple of inaccuracies.
Okay.
No big deal. I really like what you're doing here. It's really great to be able to see specialized applications being handled in a particular way. Really nice to see the trade-offs. Question for you. The tests that you did were using individual jobs that were really quite small compared to the size of the cluster. I wondered if you explored jobs that, let's say, had 400 node cluster, had maybe 200 workers in them. See what would happen with this kind of environment.
What was the question again? I'm not sure I got it.
You have a 400 node cluster in your tests, and you're running jobs with like 10 workers in them. Sure. What happens if you have a single job with 200 workers in it?
So much smaller tasks.
Much bigger jobs compared to the size of the cluster. What happens with your system, with your constraints?
I think that's what we
Did you try it?
Yes, we did try it, right? So here, this is what we're trying to do here. So
a single job that fills half the cluster, what happens?
So pretty much what will happen is our scheduler will have to consider in a single cycle the placement of the whole cluster, right? So this is pretty much what we do where the fraction of utilized resources is 100% here. So this will take several seconds, but the scheduler will actually work. Yes, we have considered that.
Okay, let's talk offline. I was more interested in the behavior around the constraints
Sure.
and what fraction get met. Thanks.
But also what I want to mention is that ILP solvers are becoming more expensive when it's fully utilized, so I agree. There will be a bottleneck there, but it will finish, right? It will run.
Hi, Junior Park from PMU. Can you describe a little bit about like how the LRA scheduler communicates the scheduling decision to the capacity scheduler?
Yes, so we pretty much follow the two-scheduler design. The concept is that the LRA scheduler periodically makes some scheduling decisions, and then these scheduling decisions are pretty much containers predefined with predefined locations, right? Is that like in Yarn is like resource request with predefined location, predefined machines, and then the task-based scheduler is obligated to follow these directions. If something doesn't work, for example, the cluster state might have changed during this cycle, right? So if that doesn't work, we resubmit the LRAs and we reschedule, right? That's how we do it.
Thank you.
Yes.
I have a question about fairness and preemption in your solution. Because usual situation when your cluster is highly loaded with task-based and you try to run some long-running application and you have no space for it, so you need to run some preemption. For example, you use some usual strategies in Yarn for preemption, but preemption is quite complicated task for long-running application. You can't preempt HBase, for example, or Storm because your applications that use it just may fail and it may be production. How do you overcome this problem? How the preemption works in your system?
Okay, good question. So currently we don't actually support preemption, but we actually thought about reservation. So reserving a specific amount of resources for LRAs. What actually works right now is we consider that all the analytics tasks apparently end up like in really short periods, in a matter of seconds. So even though the cluster might be fully utilized, there are periods that the tasks, at least the analytics tasks, go down and up. So there is a chance for our LRA scheduler to allocate resources for us, right? And the fairness is actually handled by our traditional task-based scheduler anyway, because the allocations all go through there, right? So all the policies and the production hardened configuration are already there. So we take advantage of those. That's what I'm trying to say. And this was one of our requirements, actually.
Okay, thank you.
Okay, so we're done. So thanks again, all the speakers.